Share my screen. And we're going to jump back into some of these examples. All right. I don't know about y'all, but this weather is amazing. I'm loving it. Where do we stop off? We stopped here. Is that right? What did we do? We did all of these except for the ones that we had planned on doing over here. Is that right?
Yeah, I think we stopped at 7.44.
But we didn't have to do it on another sheet, didn't we?
Yeah.
Yeah, all right. I'm gonna combine all. That's one of the reasons why I didn't upload the notes from the other day, because I need to combine everything on one document. So I'll do that today. And I'll have both Wednesdays and today's lecture uploaded, like the YouTube recording, and I'll upload the notes as well. But we're gonna start, we're gonna go right here. I think we said we were gonna do B and C. Is that right? Did we say B and C?
We said A, C, and E.
A, C, and E? Oh,
Mm-hmm.
let's do that then. A, thank you. C and E. So all of these are, if you look at the product, right? All of these are elimination reactions, like every last one of them. The question is whether or not it's E1 or E2. So you can look here, you can see these are done in sulfuric acid, A, B, and C, right? And here, these are done in a protic solvent, ethanol, right? So more than likely, all of these are gonna fall into the category of E1, because if it was E2, there would be a base present, a really strong base, like sodium hydroxide, like potassium terbutoxide, like sodium amide or something like that. So let's look at A. We're already working on the assumption that it's an E1. So I'm gonna cut it and then we're gonna move it down so we can work through it. All right, we're gonna put it right here. All right, so with this being E1, let's start here. And I'm only gonna go through, well, I'll go through the mechanism for all of them because two of them are gonna have a slightly different outcome than what's expected. All right, so here we're gonna start here. What's gonna happen when you put that OH in the presence of sulfuric acid?
It's going to deprotonate the alpha proton.
Right, it's gonna do, yeah, you're right. It's gonna do proton transfer with that acid. Right, so I'm gonna, and what I'm doing in that step, even though it's not a part of the rate determining step, is I'm making that water, that OH, a better leaving group. Right, so now I have that plus this. And this intermediate obviously is going to lose water as the leaving group and give me a carbocation intermediate. Tertiary. Right? And then my product, you can see what the product looks like. I'm just going to draw it that way. How do I get to that from this intermediate? What proton do I need to remove to get to that product?
You need to remove the alpha proton, right?
Yes. Which one?
Mm.
Alpha protons on both sides of that carbocation. I got them here and here. but look at the product and tell me which one needs to come off.
The one on the right or the bottom?
The bottom.
Yes, that's the proton that I need to remove. This one right here, boom, like that. And then that pair of electrons is gonna come here, right, to put that pi bond in. Y'all following that?
Yes.
So in this case, it has to be the conjugate base that's going to do the proton transfer. Is it Carlin or Carolyn?
Carlin.
Carlin. That was you earlier, right? Asking about that.
Mm-hmm.
Yeah. So in this case, you don't have any competition because it's concentrated sulfuric acid. So it's basically neat, right? There's no dilution. So there's no water to compete with the acid. Right, other than the water that left. Right, but in this case, it's going to be the conjugate base that does the proton transfer. All right, let's do C. Let me cut it. All right, if you look at that, how it is, what's the expected elimination product? What do you think? Look at where the OH is. That's where your carbocation is going to end up. What would you expect? Where's the alpha proton to that OH? Wouldn't it be right here?
Like the bottom?
Yeah, at the bottom.
Let me fix that up. That's gonna slop. It can't be here, right? Because there's no hydrogens on that carbon, right? So it's only that one. So the expected
You said
product,
because there's no what on the carbon?
no hydrogens.
Okay.
That's a quaternary carbon. It's got 4 groups already on it.
Okay.
Yeah. Right. So the expected product under normal circumstances, you would expect to get this as a product. But that's not observed. All right, look at the product that we do get. And we're going to go through this mechanism to find out what happened. So let's do that. So I can steal this. Right, what's the first thing that's going to happen here with that sulfuric acid? Is anything different going to happen than what happened in the first example?
No. Proton.
No.
Right, you're going to do proton transfer here. Like so. And then you're going to get to the intermediate hydronium ion. Right, which is going to lose water as the leaving group. Nothing changes. All right. Come on, Russell, get it together. So now I have a plus charge on that carbon, right? Based on what you see in the product, right? What does it look like happen in that product? Right here.
Rearrangement.
Some type of rearrangement happened because one of those methyl groups from up here moved, didn't it? All right, so when you look at this carbocation, this is a secondary carbocation. Now, if you put the plus charge here, that will give you a tertiary. And anytime you see a rearrangement like a methyl shift or a hydride shift or something like that, it usually happens to give you a more stable carbocation. So in this case, what we actually see, or what we actually get, and why we don't get that expected product, is because of what we call a methyl shift. Which is a type of rearrangement. Right? So one of these methyl groups is going to actually move with its electrons. So the carbon and the electrons are going to move to here. Right? And what that's going to give us, that rearrangement, is going to give us this. And now my plus charge is here. Yes, no?
Yes.
Yes.
Can you explain that one more time? Why does the rearrangement happen?
Oh, okay, great question. So anytime you do a rearrangement like this, where you have a cation that is rearranged, is normally to give you a more stable cation. So that's a tertiary carbocation, secondary up top. This is a tertiary carbocation, which is more stable.
Okay, got it.
So that's why I rearranged like that, to give you that tertiary.
Okay.
And then this now is, I have a proton here that can come off, right? That's going to be my alpha proton. I also have a set of alpha protons here, but remember, we're following Zaitsel's rule, and that red proton, if I take that off using that conjugate base, I'm just going to abbreviate that as CB. If I take that off using the conjugate base, right, that's going to give me a tetrasubstituted alkene in the product, right? That's what the product is up top. It looks like this. Are y'all following? So that rearrangement happened on purpose. It happened in order to stabilize the carbocation intermediate. And then it's the more stable carbocation is the carbocation that got where the elimination took place at. Right there. Here. So that rearrangement happened to give you a more stable carbocation from a secondary to a tertiary. And then in the next example, you're going to see something similar. Well, no, never mind. In B, I want you to work B on your own. I'm going to highlight this one, because B is very similar to C. All right, let's go ahead and do E. Let me cut it out and drop it down below.
I have a quick question about the one
Yeah.
we just did. So going to like the methyl shift,
Mhm.
and we moved it, so your red arrow, we moved it to the bottom. Is it not moving flat? Like, are you saying the hydrogen is what makes the double bond?
You mean, are you talking about right here?
Yeah.
Yeah, so after the methyl shift, that's when you do your elimination. So this part right here is the conjugate base of sulfuric acid coming in to do proton transfer at that alpha proton. So it's pulling off the proton, and the electrons in the CH bond are going between these two carbons right here to give you your alkene.
Okay. Thank you.
Mhm. All right, let's look at this last elimination. It's still going to be E1. It's a tertiary carbon. Let's see what we get. So this is iodine. Of course, the first step is loss of leaving group. Got tertiary carbocation. Is that right? And now we just need to, I'm gonna put this in as an intermediate. Right. So that's that. And then we have sodium ethoxide, which is not a great base, but it is in solution. And notice it's in solution with ethanol. So it's in solution with its conjugate acid. And so it's going to be the sodium ethoxide that comes in and pulls off the alpha proton. Right, to give you your product. I'm just going to write it. Right, but it's still an E1 because the product solvent and the tertiary substrate give it away that it's an E1. And you see the elimination product, right? Anytime you make a multiple bond and the product, whether it's a double or triple bond, that's always going to be the result of some type of elimination. All right, questions about these examples before we move on to the next section? This month is over. Wow. All right, let's go ahead and take some questions in the next section. I want you to work on, notice this says nucleophilic substitution, right? So you're not guessing about whether it's substitution or elimination. So I want you to do A, D, C, and F. And also tell her what type of substitution. So this is on your own, those 4 problems. And then also add in what mechanism. All right. So let's go down to, I really think this is the last part of this section. Let's go to 749. And we're going to do B, E, and I. Let's do that. So it says draw the substitution product that results when butyl bromide reacts with each nucleophile. So we can just draw that down here. Don't do that. It's gonna be a mess. I'll just put it here. Put another page in. All right. So this is my substrate. You can see that it is a primary substrate. It doesn't give us any solvent or anything like that. But if I react this with SH, what am I going to get? right? Anybody? Don't all speak out at once now. The internet might shut down. What do I get from this reaction? And what type of reaction is it? Since it's on a primary substrate. And it's telling you right here that it's a substitution.
So it'll be SN2.
Good.
And you're substituting that S with the bromine, the SH, I mean.
Good. It says SN2, right? Anytime you have a primary carbon like that, it's going to be and it's a substitution, it's going to be SN2. What about the second reaction?
Is that also SN2?
Yeah, your substrate is primary.
Yeah.
So every one of these is going to be SN2. That's right. What's the product going to look like? If bromine is my leaving group, all I'm doing in this example is swapping out the leaving group with the nucleophile that's given. So here, right, the alkyne is the nucleophile. Right, and then here, remember, anytime you see sodium, it's a counter ion. So it's Na plus and then N3 minus. This is what is called an azide. Very, very good nucleophile. It's actually a precursor to making carbene diazo compounds, which can be used to make carbenes for a lot of different applications. But what's the product?
N3.
So N3 is here, right? Where bromine would be. Good. All right, so I want you to work through the ones I had up here, drawing the products. If you have to put the arrows in, do it. But the more reps you get, the better you're going to be at this. Like, it's no secret about that. All right, let's do, we're going to do.
Could you scroll back up just a little?
You're here?
Yeah, thank you. Okay.
All right, let's do 755. I'm gonna cut this out because we need to talk about this. Right, so it's asking us to rank the nucleophiles in order of increasing nucleophilicity. So from worst to best, right? And this is a video that I sent out like early. Hopefully you watched it or you read the section, right? But there's some trends for nucleophilicity that we have to remember. And the trends are solvent dependent. So solvent dependent. Right? And a protic, well, let me start with aprotic. So a polar aprotic solvent, right? It is decreasing from left to right and decreasing from top to bottom. Right? That's the trend for the nucleophilicity. So as you go from left to right, the the nuclear felicity is getting worse. And as you go from top to bottom, the nuclear felicity is getting worse. And if it's in a polar protic, it's increasing. I'm sorry, decreasing again, left to right. And then from top to bottom, oh, that's gonna get cut off. Shrink this down some. Right, so if it's in a polar protic solvent, it is decreasing from left to right, and it's increasing from top to bottom. And that's due to solvation, right? It's due to solvation. As the atoms get bigger, the atomic radius increases in a polar protic solvent. It makes it harder for the solvent to trap it. So that's why the nuclear felicity is increasing going from top to bottom, because the atomic radius is also increasing. So let's look at the examples. And it's asking us to rank them in order of increasing nuclear felicity, right? So when you look at carbon, oxygen, and nitrogen, right? You know, the periodic trend is C, N, O, and then fluorine, right? So when you look at that going across the periodic table, which one of those is going to be your best nucleophile? If nuclear felicity is decreasing,
C.
left to right, carbon. So carbon is going to be the best. And then which one is going to be the worst?
Fluorine.
O. Oxygen.
Oxygen. Are y'all following that? Because nuclear felicity is decreasing from left to right. Anything to the right of the atom is going to be a worse nucleophile. So for carbon, since nitrogen is to the right of it, it's going to be a worse nucleophile. For nitrogen, since oxygen is to the right of it, it's going to be a worse nucleophile than both of those, right? So carbon is the, I want to try to squeeze this in here. All right, let's do this. I'm gonna just do a little legend out here. So yellow is gonna be my best. Red is gonna be the worst. That way I don't have to try to squeeze in the best and worst for each one of these examples. All right, now let's look at B. It says it's water, hydroxide, and then the sulfur anion, but it says it's in methanol. Uh-oh, let me not screw that up. It's in methanol. Methanol is what type of solvent? Protic or aprotic?
Protic.
It's protic. All alcohols are protic. So if this is a protic solvent, which trend is this going to follow?
Decreasing left to right, but increasing top to bottom.
Good, excellent. So think about this. So oxygen is here, sulfur is underneath it. So which one of those is going to be the best nucleophile? Because notice oxygen is in both the OH, the hydroxide anion, and in water. So what you're comparing now is oxygen and sulfur in a protic solvent. So which one is going to be best?
The
So
sulfur.
sulfur, because it's down the group, it's under oxygen. And so in a protic solvent, sulfur is a better nucleophile. Now, between water and hydroxide, we have to make a choice, right? Remember from part one, a nucleophile can be negative or neutral, but a negative nucleophile is always more reactive, right? So if you had to choose between something that's negative and something that's neutral, with the same atom being the nucleophilic atom, in this case, oxygen, what would you pick?
OH minus.
Right, so that means that water is the worst one. Following? Since OH minus is a better nucleophile than water, water is the weakest of all three of those nucleophiles. Does that make sense? Yes, no?
Yes.
All right.
Yeah.
Now, let's do C. Let's do C. So we're in methanol. Again, we already said that's protic. So if you can look right away at these and pick the best one, right? Because if it's in a protic solvent and you're comparing sulfur to oxygen, which one is going to be better?
The first one.
Sulfur. Good. Now let's look at the two nucleophiles that are given. I need some space. Let me, I'll just add a page, it's cool. All right, so right here, we have CH3, this is CH2O minus, and then CH3. When you see that COO, that's an abbreviation for carbonyl. All right, so now we're looking at these two potential nucleophiles. Which one do you think is better? The charges on oxygen in both cases. What do you think?
The bottom one.
Okay, why do you say that?
Because it got two oxygens attached to it.
That's a good assumption. But let's think about what nucleophiles do. What do they do? Do they donate or do they?
Donate.
They donate. If this oxygen right here can do resonance, that means that those electrons are less available to be donated. So the resonance is actually going to attenuate the nucleophilicity. Right, the fact that those electrons are tied up in resonance, this is going to be better. Right, does that make sense?
Yes.
If those electrons are doing resonance, then they're not going to be as available to donate to an electrophile. All right, so we go back to the problem of those two, which one is the worst?
The last one.
Acetate and that's wrong color, sorry. Right. So again, the sulfur nucleophile is best, and then acetate is the worst. All right, let's do one more, and then we're gonna do a couple of these other problems, and then we'll be done with this section. Let's do E. It says OH, F, and chlorine and acetone. All right. So which one is the worst? Remember the trend, decreasing from left to right. This is a aprotic solvent.
Chlorine.
Chlorine is going to be worse. Is that right?
Yes.
And then between oxygen and fluorine, oxygen is better because it's to the left of, I'm sorry, yeah, to the left of fluorine. Because it's decreasing from left to right, and it's decreasing also from top to bottom. All right, is that making sense?
Yes.
All right,
Yes.
so let's do one, how much time we got? 7 minutes. Let's do one problem, two problems from up here. Yeah. Let's see. So we'll do B and C, and then we'll do because all of these are E2, so it gave you that. And then we'll do D down here. So let me cut those out. All right. Didn't do what I wanted to do, but we'll start with B. All right, it just says draw all constitutional isomers. All that means is, let me get the base on there too. Because DBU is it's a strong base. I think it's on that list of bases that I gave you in that elimination video as well. So here, what am I looking for? I know it's an E2 because the problem told me it was an E2. What am I looking for?
Group.
Bevan group,
Alpha
and then
proton.
alpha protons, right? So that's going to be here. One proton right there, right? So now if I were to ask you just to draw the product, where would the double bond end up in this case?
And to the left of the CL.
It's going to end up right here, isn't it? Right, so now, when I draw that product, right, that's what that product is going to look like. That, and it's E2. It told you that was E2. All right, let's look at C. What about C? I'm gonna not go through the actual mechanism, but let's see if we can figure out how many products we're gonna get. Look, where's the leaving group?
I.
Iodine, good.
I.
All right. How many alpha positions are there to this carbon right here? Because this is the carbon where the leaving group is attached, right? Right here. How many adjacent carbons are there to that with hydrogens on them?
2.
2.
So you saying this one and this one?
Mm-hmm.
Yes.
What about this one?
Yes.
Isn't that also alpha?
Yes.
It's next door, right? So you actually have 3 alpha sites here. So you're going to get three products. That's why it says draw all the constitution. That's why the product says draw all the constitutional isomers. It's kind of I'm not going to say a trick question, but it's forcing you to look at everything that's here. So that's that. That's one. The other one is gonna be with the double bond on the other side. Like that. And then there's gonna be one more where the double bond is here. Are y'all following? So this is, I'm gonna label them. That'll be A. And then let's call this one B, which would be right here. And then this would give us C. All right, so all those are E2 products. All right, I'm gonna leave, what else? Which one did I say? And I'll get these notes combined and all and taken care of and all that stuff today, and I'll upload it. So I'm gonna leave you with D on that last example. And we're gonna stop. We have a new section, but I don't want to start it today because we only got 2 minutes left. So we'll start that new section on Monday, dealing with conjugated dienes. I'll send you some videos over the weekend to watch. If you look at the syllabus, you can see the section and the chapter and the section that we're going to be in, so you can read up on it. And Monday, we're going to hit it. We're going to talk about 2 different reactions that happen with conjugated dienes. All right, any questions?
Can you scroll back down to the